Somewhere off the coast of Yorkshire, 80 miles out, give or take, there is a hole in the seafloor, not a small one, 3 kilometers across, surrounded by a ring of cracked and fractured rock that spreads 20 kilometers outward in every direction, and buried 700 meters deep under layer after layer of sediment that accumulated over tens of millions of years. Nobody knew it was there until the year 2002, and once it was found, honestly, nobody could agree on what made it. That argument lasted 24 years. Professional geologists, formal votes, journal papers going back and forth, and a structure that just sat there, unresolved, while the North Sea went about its business of oil platforms and fishing trawlers and shipping lanes, completely indifferent to what was buried underneath it. Then, in the year 2025, someone found something in an old cardboard box. 2 grains, 2 microscopic grains of damaged mineral pulled from archived rock samples that had been sitting in storage for decades without anyone examining them closely. And those 2 grains ended the argument. What made that crater was an asteroid, roughly 160 meters wide, traveling at several miles per second. It hit the floor of an ancient shallow sea, 43 to 46 million years ago. And the impact blasted a curtain of rock and water 1.5 kilometers into the sky, which then collapsed back down and sent a tsunami more than 100 meters high racing outward across the ancient North Sea, 330 feet. That is how tall the wave was, taller than most skyscrapers most people will ever stand next to. And until very recently, the scientific community's official position was that this probably did not happen. To understand how a 24-year argument even starts, it helps to know a little about what the North Sea looks like underground. The seafloor there is not simple geology. Buried beneath it, deep beneath it, are ancient deposits of something called zechstein salt. These are massive layers of salt that formed hundreds of millions of years ago when ancient seas evaporated. And the thing about salt, geologically speaking, is that it moves. Slowly, over millions of years, under enough pressure from the rock above it, salt flows. It shifts. It pushes upward, deforms the layers above it, and can create dome-like structures in the rock that look, on a seismic scan, a bit like something violent happened there. This matters because when the Silverpit structure was first discovered, the people who looked at it and said asteroid crater had to compete with the people who said salt tectonics. And the salt argument was not a fringe position. It was grounded in real, well-documented geology that anyone familiar with the North Sea would have considered a reasonable starting point. What's weird is, the structure found in 2002 did not look like a simple salt dome, not at all. The shape was too specific, too circular, the raised peak in the center, the concentric ring faults spreading outward across 20 kilometers. These were features that matched the profiles of known impact craters on land, on the Moon, on Mars. Phil Owen, working with Production Geoscience Limited, and Simon Stewart, who was with BP at the time, were the ones who spotted it while reviewing oil industry seismic survey data. They published their findings. They put the asteroid hypothesis on the table, and the geological community kind of split in half. The problem was evidence, specifically the absence of a very particular kind of it. When an asteroid hits rock at hypervelocity, that word matters. It means traveling at several miles per second. The collision generates pressure waves of extreme intensity. The numbers involved are almost impossible to picture, 10 to 13 gigapascals. That is the kind of pressure that physically deforms minerals at the atomic level. It fractures the internal crystal lattice of quartz and feldspar in a very specific pattern of parallel lines, structures called planar deformation features, or shock lamellae. These cannot be faked. No salt movement, no volcanic process, no tectonic compression anywhere on Earth produces pressures in that range. They are, in the most literal sense, a fingerprint left by an impact. And at Silverpit, nobody had found them. That absence was the whole ball game. Without shocked minerals, you could not definitively rule out the salt explanation. The impact team had the crater's shape, they had the ring faults, they had the central peak, but all of that could theoretically be argued away by a patient geologist who knew their salt tectonics. For 7 years, the debate ran through journals and conferences without landing anywhere. Then came 2009. At a scientific gathering that year, a formal vote was held among attending geologists. The question was essentially, is Silverpit an impact crater or not? The majority voted no. Think about that. A room of professional geologists, People who spend their careers reading rock layers and interpreting seismic data looked at everything known about Silverpit at that point and concluded, by majority opinion, that the asteroid hypothesis was probably wrong. According to a report in Geoscientist magazine, the skeptics carried the day. The salt explanation, or at minimum, the not enough evidence to confirm an impact position, won the room. This was not a dismissal by amateurs. The people in that room included researchers who had been tracking the Silverpit question since it first appeared in the literature. Professor Gareth Collins of Imperial College London was there. He would later be one of the researchers who helped confirm the impact. He believed in the impact hypothesis even then. He said as much afterward. But the vote did not go his way. And after that, Silverpit kind of disappeared. Not from the literature entirely, it remained a known contested structure, referenced occasionally in papers about North Sea geology. But no one was actively pursuing new physical evidence. No new sampling of the crater was attempted. The question sat officially open and practically ignored for over a decade, which, honestly, is how a lot of science actually works. Resources go where the consensus points. If the prevailing view says, probably not an impact, the funding for proving it is an impact tends to dry up. The structure stayed buried, both literally and figuratively. Somewhere around 2023, Uisdean Nicholson at Heriot-Watt University in Edinburgh started paying close attention to Silverpit again. He had access to something the original researchers in 2002 did not: a new generation of three-dimensional seismic imaging. Think of seismic imaging as an ultrasound for the planet. Sound waves are sent down through the sea floor. They bounce off different rock layers at different depths, and the returning signals are processed into a three-dimensional map of what is underground. The technology had improved dramatically since the early 2000s. The resolution was sharper. The detail visible in the buried structure was far clearer. And what Nicholson and his team could see in the fresh images was internal crater architecture that matched impact structures elsewhere on Earth in ways that were hard to dismiss. The crater bowl was revised in size, narrower than some earlier estimates, approximately 3 kilometers across rather than the larger figures sometimes cited. The central raised block was visible. The outer fault zone, spreading 20 kilometers from the center, showed a pattern consistent with the shockwave propagation you would expect from a hypervelocity impact, and the approach angle of the asteroid could be inferred from the asymmetry in the fault patterns. The object appeared to have come in from the west at a low, shallow angle rather than dropping straight down. That seismic work was compelling on its own, but Nicholson knew it would not be enough. The 2009 vote had already proven that structural evidence, without the physical shock metamorphism fingerprint, would not close the argument. So he went looking for the samples. Oil exploration in the North Sea had been drilling wells through that region for decades. One of those wells, Exploration Well 4325-1, drilled years earlier by the oil industry, had passed through rock at exactly the right depth. The drill cuttings from that well had been archived. They were physically accessible, and as far as anyone could tell, no one had examined them systematically under a petrographic microscope, looking specifically for the shock minerals that would confirm or deny the impact hypothesis. Nicholson found the archived samples. He looked, and in a cardboard box of mixed rock fragments, chips of this, pieces of that, the ordinary detritus of a routine oil exploration drill, he found 2 mineral grains. 1 quartz, 1 feldspar, both carrying planar deformation features, both showing the parallel internal fracture structures that form only under 10 to 13 gigapascals of pressure. Only one thing in nature produces that pressure: an asteroid impact. He would later describe the effort as a real needle in a haystack, which is one of the more restrained ways you could describe finding the evidence that ends a 24-year argument inside a box of old oil samples. The study was put together by a research team that included not just Nicholson, but contributors from institutions across multiple countries: Yane de Jong, Anderson, Gareth Collins, the same Collins who had been in that 2009 vote, Alex Gillespie, Thomas Kenkman from Universität Freiburg in Germany, Tom Dunkley-Jones from the University of Birmingham, James Frankel, Veronica Bray from the University of Arizona, and Sean Gielick from the University of Texas at Austin. International, independent, and covering every major technical aspect of the investigation: physical sampling, seismic interpretation, numerical modeling, and comparative planetary geology. It was submitted to Nature Communications and published on the 20th of September, 2025. And you have to appreciate what those 2 grains actually represent. It is not just that they confirmed the impact hypothesis, it is the specific pressure they record, 10 to 13 gigapascals. The internal fracture patterns in those minerals do not form under normal geological stress. They do not form from volcanic activity. They do not form from salt moving. They form when a shock wave from a hypervelocity impact passes through rock so fast and so violently that the mineral's internal structure gets literally rearranged. The process is called shock metamorphism, and those two tiny grains are carrying proof of it that had been sitting in a storage facility, unexamined, for years, possibly decades. What came next in the paper was the reconstruction of what the impact actually looked like. Professor Collins had built numerical models, computer simulations of the impact event, that he could compare against the crater's observed structure. The numbers in those simulations aligned cleanly with the pressure measurements from the shocked minerals. The model and the physical evidence told the same story, independently, and the story they told was not small. A rocky asteroid, estimated at approximately 160 meters wide, not enormous in planetary terms, not remotely close to the 6-mile-wide object that ended the dinosaurs, but still roughly 1.5 times the length of a football pitch, traveling at several miles per second, struck the floor of a shallow, warm sea. This was the Middle Eocene epoch, roughly 43 to 46 million years ago. England looked nothing like England today. The southern North Sea region was subtropical. Shallow, warm seas extended across what is now the English Channel and the surrounding area. There was no Yorkshire coastline in the modern sense, just water, warm, shallow water, over what is now one of the most heavily industrialized stretches of ocean on Earth. The asteroid hit that water, and the seabed beneath it at hypervelocity. The initial explosion was essentially instant. Rock and water vaporized at the point of contact. Within what the models describe as a matter of minutes, a curtain of debris, rock fragments, sediment, steam, vaporized material, was launched 1.5 kilometers upward into the atmosphere. That is higher than the tallest mountain in the United Kingdom. That column did not stay up. As it collapsed back down into the sea, and it collapsed fast, it shoved an enormous displacement of water outward from the impact point. The wave this generated exceeded 100 meters in height, over 330 feet, and it moved outward across the ancient sea in every direction, 80 miles from shore. That would have given the coastline roughly 12 minutes before a 330-foot wall of water arrived. The crater did not sit quiet after the initial strike either. Seawater rushed back into the excavated bowl with enough force to reshape it. Blocks of ejected rock fell back in and around the structure, leaving smaller secondary craterlets visible in Nicholson's seismic images. And deep in the center of the crater, where the chalk layers had been exposed to the extreme heat of the impact, something unusual happened. The rock underwent a process called devolatilization. Heated carbonate rock releasing trapped gases, probably carbon dioxide mixed with steam, and this flattened what would otherwise have been a raised central peak, leaving behind a distinctive flat zone with small pits in it. That gas release signature is visible in the seismic data. It is not yet confirmed by direct drilling, and Nicholson's team is careful to flag it as a hypothesis rather than a fact. But it is there in the imaging, and it hints that the impact may have triggered a secondary geological event in the chalk layers that nobody had accounted for in previous impact hazard models. And now comes the part that genuinely sits uncomfortably. The study was published in September of 2025, peer-reviewed, Nature Communications. That is not a minor journal. Multi-institutional, international authorship. 3 independent lines of evidence, all pointing to the same conclusion. Physical samples, seismic imaging, and computational modeling that aligned with the sample measurements. And yet, the broader public conversation about this confirmation was slow, quiet, compared to what the actual discovery warranted. Part of that is just how science communication works. A confirmation study resolving a 2-decade-old argument is not the same news cycle as a brand new discovery. Editors make judgment calls. Scientists confirm old crater is actually a crater, does not have the same headline energy as scientists discover crater. Even though the confirmation itself, the 24-year argument ending, the formal expert vote being overturned, the needle in a haystack sample recovery, is genuinely the more interesting story. Nobody talks about what it means that the experts voted wrong in 2009 either, not in any critical way. The vote happened, the vote was wrong, the science corrected itself, end of story. Which is the correct scientific framing? This is how the process is supposed to work after all. Evidence changes consensus, but it glosses over something worth sitting with. For over a decade, the default scientific position on Silverpit was that it was probably not an impact crater. That meant no resources flowing toward confirming it. No urgency around examining those archived samples. An old box of oil well cuttings sitting in storage while the question it could have answered gathered dust alongside it. And here is the thing that is hard to shake. How many other boxes are there? Nicholson found those 2 grains through deliberate, targeted searching. He knew what he was looking for and where to look. But the North Sea alone has been drilled by the oil industry through hundreds, probably thousands, of wells across decades of exploration. Many of those well cuttings are archived. Many of them have never been examined for shock metamorphism. No one has ever had a reason to look at most of them. There are only 33 confirmed impact craters on the entire ocean floor of this planet. The ocean covers 70% of Earth's surface. That is a number that is almost certainly wrong, not because the craters are not there, but because the ocean floor recycles itself through plate tectonics, buries evidence under sediment faster than continental crust does, and has been examined in detail only in places where the oil industry had economic reasons to drill. Silverpit survived because it was buried deep enough, fast enough to be protected from erosion and plate movement. It waited 43 million years to be found, and then it waited another 24 years to be confirmed. And the only reason confirmation finally happened was because one researcher at Heriot-Watt University went looking in archived samples that had been sitting in a box, correctly labeled and completely unexamined. That is both a story about science working, slowly, correctly, eventually, and a story about how much we are probably still missing. Dr. Nicholson said, after the confirmation was published, that Silverpit is now one of Earth's clearest marine impact stories. And that is accurate. The crater gives scientists something genuinely rare, a preserved, detailed sequence of what happens when an asteroid hits a shallow sea, from the initial impact through the crater collapse, the flooding, the gas release, the burial. That sequence is hard to reconstruct on other planets where drilling down is impossible. Silverpit exists, is accessible through existing well infrastructure, and is now confirmed. Scientists can use it as a real-world reference case for understanding how asteroid impacts shape planetary surfaces. Collins said after the study came out that the confirmation opens up the exciting job of using the amazing new data to learn more about how impacts shape planets below the surface. That is the scientific framing. Forward-looking, constructive, the argument settled, and the next chapter beginning. And the Nader crater comparison is worth dwelling on for a moment. Nader was identified off the coast of Guinea in West Africa, also through oil industry seismic data, also by researchers at Heriot-Watt, the same institution that led the Silverpit confirmation. Nadir is estimated at 400 meters or wider. It formed approximately 66 million years ago, possibly at the same time as the Chicxulub impact. Silverpit and Nadir are now the 2 most completely mapped confirmed marine impact craters on Earth, and both came out of the same general methodology: oil industry, 3-dimensional seismic data, physical sampling, computational modeling. The same approach that spent 24 years failing to confirm Silverpit is now the template for identifying more. But the unanswered question, the one that does not have a clean resolution, is the chalk layer. Deep in the center of the Silverpit crater, beneath where the central peak would normally be, the seismic images show something unusual. The heated chalk underwent devolatilization, gas release, carbon dioxide mixed with steam, the models suggest, escaping from the carbonate rock during and immediately after the impact. Nicholson's team notes this in their study and explicitly flags it as unconfirmed. It will require direct drilling into the crater to verify. But if it happened, it adds a layer to the impact story that the scientific community has not fully accounted for. Marine impacts into chalk-bearing seafloors may not be purely mechanical events. They may trigger secondary geological processes, gas eruptions, chemical changes in the rock column that compound the initial damage. Nobody knows. They need to drill to find out. And until they do, that part of the Silverpit story sits unresolved. The impact is confirmed. The tsunami height is modeled. The asteroid's size and approach angle are estimated. But the full consequences of what happened in those chalk layers 43 to 46 million years ago, that part remains open, which is, honestly, where science tends to actually live. Not in the clean confirmed facts, satisfying as those are, but in the questions those facts open up immediately after. The argument is over. 2 grains in a cardboard box ended it. But the investigation, the one that actually answers what Silverpit can teach about asteroid impacts and planetary geology and the consequences of space rocks hitting shallow seas, that investigation is just getting started. And given that it took 24 years just to confirm what the crater was, you have to wonder how long the next set of answers will take. There are 33 confirmed marine impact craters on the ocean floor of this planet. 70% of Earth is ocean. The number 33 is almost certainly not close to the real number. The question is, how many other Silverpits are sitting in archived well-cutting boxes right now, correctly labeled, never examined, waiting for someone to look? So if you've got a theory on that, or if you think there's a reason those boxes stay unexamined, drop it below.